Thank you very much. So thank you to all for being there, and to the scientific committee for allowing me to present to you this joint work with Olivia Carmelo. So on a generalization of a factorization system, you may already know for geometric morphisms. So there are several well-known factorization systems on the two categories of Grothendieck topoi and geometric morphisms. The best known is the surjection and Belin factorization, but also one we just heard of, at least partially, is the interconnected localic factorization system, and a bit lesser known the pro-etale factorization, for instance. Those factorization systems allows you to decompose geometric morphisms into a pair of morphisms which belong in the left and right class with nicer dual properties. And this is what I said. Just what I said is the generality of factorization system. But in the two categories of Grothendieck topoi, since geometric morphisms are pairs of adjoint functors which convey dual information depending on the sense you read them, in the sense that if you read them in the sense of their right adjoint, the direct image, you may convey geometric information, while if you read them in the way of their inverse image part, you may read algebraic information. Then it means that left and right classes of factorization system may be, their dual property may be read in two different ways. So either from a geometric point of view, in which the left class will express something akin to connectedness in some sense, while the right class will dually express some kind of truncatedness. And but dually from an algebraic point of view, the inverse image part of right maps will behave as functors that generate their codomain through some operation. And dually, inverse image part of the left class, of a morphism in left class, will behave as functors that are closed under some operation. And it happens that some factorization systems only hold for restricted class of geometric morphisms that have additional data allowing to define what will play the role of factorization. And in particular, an important one is the so-called connected etale factorization, which return in some sense an object of connected component of a geometric morphism. And the problem so is that it holds only for the class of geometric morphism which have a well-behaved notion of object of connected component. But in this talk, I will show you that in fact this restriction can be solved, and that can be generalized into a factorization system for any geometric morphism as soon as we correctly understand the generalization of the left and right class. So first I will present you a bit generality on the connected etale factorization and what it means, and I will give you some ingredients to generalize this construction, and spoiler, as you may see, it will involve a profiter delimit. And then I will show you how to process the factorization and give you some properties of the left and right class in this factorization. So first, it's a fundamental theorem of topos theory that if you take a topos and an object in this topos, the slice over this object is again a topos, and the pullback functor is the inverse image part of a geometric morphism, which may have several names, but often is called the etale geometric morphism as this object. And we call etale geometric morphisms that are actual equivalents of this form. And if you see object in a topos as sheaf on some space, this construction corresponds in a sense to the etale space over this space in which you take a sheaf. And the point is that those etale geometric morphisms have a special classifying property relative to what we call global elements. So global element, which also may be read as a global section in some sense, are morphism from the terminal object of the topos into a given object. And a morphism of global element is simply an underlying morphism that make element communes. And the point is that global elements of a fixed object are in correspondence with the section of the corresponding etale geometric morphism. And this generalizes across geometric morphisms in the sense that factorization of a geometric morphism through etale geometric morphism corresponds to global element. That is, if you have a geometric morphism F, and if you factorize up to an invertible two cell through an etale geometric morphism, then you can show that the left part corresponds uniquely to a global element of the inverse image of the object at which you took the etale morphism. And you can show that in fact its inverse image part can be computed by taking the fiber of at a map over E, the fiber across the corresponding element. So, so you have in each a natural isomorphism that embodied what I just said, and collectively, those natural isomorphisms give you an equivalence of category between the category of global element of the inverse image of geometric morphism and the category on the right of all its possible factorization through an etale geometric morphism over its column. And you, from this you can deduce that etale geometric morphism over topos form one category, and this is related to the fact that this is in fact express something about discreteness. In fact, you can show that etale geometric morphism are discrete objects in the over topos are discrete objects in the two categories of geometric morphism over this topos, and this is because any topos believe that its objects are internal sets. But internal sets are the same as discrete spaces. And more precisely, in fact, the object of a topos corresponds to this notion of discrete internal locale. And that's why etale morphism corresponds by the correspondence between internal locale and localic morphism over the topos to the one that are discrete. But discreteness is the example of truncation condition. And if you remember what I said on the duality between connected, the geometric interpretation of left and right class in the factorization system, we can expect then that etale geometric morphism are in some orthogonality structure right to some class of morphism expressing connectedness. And this is the case. So they are indeed right to connected morphism, which were presented just in the previous one, and connected morphism are left to etale morphisms. But beware, they are not all the morphisms that are left to etale geometric morphism. And because of this, we could not expect that every geometric morphism has a connected etale factorization. So the ones that do are those what we call locally connected, which are those whose inverse image part has a further left adjoint we call the essential image, and which moreover satisfies some Frobenius condition, which is not relevant in this expose. But what is important is that those locally connected morphisms enjoy connected etale factorization, which is constructed by taking the etale geometric morphism at the essential image of the terminal object of the domain topos. And the left part is simply, under the correspondence with the global element I just told you, the name of the unit of this further adjunction. As you see, in fact, we are just using that there exists such an object, such an essential image part, which in this case here as in some sense an object of a connected component of F seen as a topos over E. And so you can expect that it could generalize to just essential geometric morphism. And indeed, it was shown recently that it does. So, but you have to generalize the class of morphism on the left and take what we call terminally connected geometric morphism, which are those that lift uniquely, those whose inverse image part lift uniquely global elements. That is, if you have a global element of the inverse image part, it must arise uniquely from a global element of the underlying object in the codomain topos of the geometric morphism, and also in a way that is functorial, relative, and peaceful, relative to morphism of elements. And you can show that those are exactly the morphisms that are left orthogonal to etale morphism. And you can show then that any essential geometric morphism enjoy a terminally connected etale factorization, which work exactly the same way. So but just now the left part is a bit more general than connected. And so the question is, can it be generalized to arbitrary geometric morphism? And at first hand you would say, okay, no way, because general geometric morphism don't have an essential image part. But nevertheless, there is a way. So, indeed, for an arbitrary geometric morphism, you don't have an object of a connected component. Because perhaps seen as a space over your codomain topos, this topos is not being not locally connected in any way, do not have a set of connected components. However, because there isn't a further left adjoint to the inverse image. However, you can show that any geometric morphism, while in general lacking a global, having an inverse image part that may lack a global left adjoint, has nevertheless what we call a left pro-adjoint. So recall that a category is co-filtered if any object, if it is non-empty, if any object are related by a span, and if any parallel pair is equalized. And in the category you can consider a co-filtered diagram, and you can, for a locally small category, you can consider its a free completion under co-filtered limit. And it embeds faithfully in this pro-completion. This completion we call the pro-completion. And you can then consider the notion. You can consider a notion, a generalized notion of adjunction relative to this completion. You can define a notion of right pro-adjoint as a functor which may not have a left adjoint, but has a relative left adjoint relatively to the embedding into the pro-completion. And you can show that by something which is about commutation of finite limit against filtered co-limit, you can show that axis de functor that preserve finite limit, in particular, are right pro-adjoint. So this applies in particular to the inverse image of any geometric morphism, because the inverse image are always left exact. So it means that for random geometric morphism, you have in some sense a notion of object of connected component, but rather than being a discrete object, this is something that learned in the pro-completion of your topos. So it's in some sense a pro-filtered diagram, and which is in fact just the co-filtered diagram of all global elements of the inverse image. And then, if you have such a diagram, you can take its limit. And the big category of Grothendieck topoi has a co-filtered limit. And they can be constructed in an explicit way. If you have a co-filtered diagram of topoi that is induced by a filtered diagram of site and the morphism of site between them over the transition geometric morphism, then you can exhibit the co-filtered limit as the category of sheets over the filtered pseudo-co-limit together with the topology that is generated jointly from the image of the topology in your different site inside the pseudo-co-limit along the pseudo-co-limit inclusion. And so we can define in particular co-filtered delimit of etale geometric morphism over a fixed codomain topos, and we call them pro-etale geometric morphism. And in particular, so remember that etale morphism classify global element, and pro-etale geometric morphism classify descent family of a global element indexed by a co-filter diagram. And you can show by closure of left class, also of right class through delimit, that they are right orthogonal, sorry, bi-orthogonal, that is orthogonal up to canonical invertible set, to terminally connected geometric morphism. So they are the good candidate to be part of a factorization system. And indeed, this is what I will show you. So there exists an orthogonal factorization system in the two categories of Grothendieck topoi, given by terminally connected geometric morphism and pro-etale. And to do that, so you take a geometric morphism, and you look at all its possible factorization through etale geometric morphism, which correspond to global element of its index image, and you take the co-filtered delimit of those etale morphisms. And the property of the delimit ensures you have a residual left map that goes from F into this delimit together with an invertible 2-cell. And what we have to prove is that it is terminally connected. But before doing that, I must just do some sanity check, because you may wonder if this large delimit is well defined. And this slide is a bit indebted to Morgan Rogers, which we had insightful discussion on this topic. And yes, this problem vanished because you can show that this large category of global element of the inverse image of a geometric morphism always admit a small initial subcategory, which will control the value of the large limit. And this relies on an accessibility argument, which is that you can find a cardinal for which your topos E is accessible, and both the element, the terminal object of both topos are compact for this cardinal. And because of this, you don't worry, this limit exists. And the proof then that the left part is terminally connected relies also on an analysis of how it looks like a global element in the pseudo-colimit over which we take sheaves to construct the delimit topos. And so what we have to do is to prove that we first prove that the functor induced by the category of category from the pseudo-colimit to F this functor, the functor induced by the property of the pseudo-colimit is the one from which you induce the left geometric morphism, which we call TF, and you can show that an object of the pseudo-colimit, which are equivalence class of triple of the form consisting of a global element of your inverse image of the inverse image of F, and a map in the etale topos over the supporting element. And you can show that it acts on such object just by taking the fibers of the inverse image of the given map along the given global element. And this expression does not depend on the representing object for the class you consider is the pseudo-colimit, because the pseudo-colimit is the localization of an max colimit whose objects are those one. And but defined this way, this define Riemann functor from the pseudo-colimit, and terminal object in the in this pseudo-colimit are exactly in fact span of this form. Because more or less what happened is that when you compute the pseudo-colimit of etale topos, you have in each slice a terminal object given by the identity of E, And when you go in the pseudo-colimit by localizing at Cartesian morphisms, they are correctly glued all together into a single terminal object, and which can be presented by any triple consisting just of a global element and the identity of the supporting object. So a global element in the pseudo-colimit is just a span of this form. And hence, if you take a global element of the inverse image part of the residual left map in the factorization, you have exactly the data of a morphism of global element of this form. And just the property of the feedback, because of the way the T of F star act on the structure. And in fact, those data are exactly what you need to construct such a span as I presented before, which is exactly, in fact, the name of a global element in the pseudo-colimit. And you can show that this extends nicely to arbitrary object of the shift topos, which is the limit, and essentially thanks to stability of colimits. And this proof that the inverse image of the residual left part lives uniquely global element, so that the left part of factorization is terminally connected. And just a word on the fact that there is a special case in which this factorization was already known, which is what we call Grothendieck-Verdi localization at a point. So when you have a point of Grothendieck topos, you can consider this co-filter limit of etale neighborhood, of formal neighborhood of this point, and this returns you the germ of your topos at this point. And the property of this germ is that this category of point is just the comma category of the category of point of your topos under this point. And this is exactly an analog of what you get when you do the germ at a point of a topological space, which is the intersection of all, is the cofilter intersection of all its neighborhood, and which happen to be the upset in the specialization order of your topology. And just a word on the fact that this factorization has a special property that is not that common for two-dimensional factorization system, which is that it manages correctly non-invertible two cells. If you have a globular cell of this form, then you can construct in a mechanical way a certain decomposition through a certain two cell on the left and an invertible two cell on the right, which relate correctly the factorization of the map F and the morphism F and the morphism G. And this is not something that is automatic for two-dimensional factorization. So I will just give a few properties of pro-etale and terminally connected morphisms. So first, so etale morphisms were localic and corresponded to discrete locale. And pro-etale geometric morphisms are exactly the ones that correspond to pro-discrete internal locale. In some sense, they are an infinitary version of the pro-finite space you meet in stone duality. Moreover, so I said that left and right class under the algebraic reading of geometric morphism could be read as something about generating and closing the sort operation. And in this case, you can show that pro-etale geometric morphisms are those whose inverse image part generates its codomain under such colimit of such fibers of the global element. And dually, terminally connected morphisms are those whose image is closed under such colimit of fibers. And so just also a word, what we did coincide back when we restrict to the world of essential and locally connected morphisms to what was already known. In particular, you can show that it is well known that a locally connected geometric morphism is connected when the essential image preserves the terminal object. And For an essential one, it just amounts to be terminally connected. And the generalization of this property is that a geometric morphism, a general geometric morphism, is terminally connected exactly when its left pro-adjoint sends the terminal object of F to the terminal object of the pro-completion. And just also a word, overset, there is no distinction between being terminally connected and connected. That is, for a geometric morphism in two sets, connectedness amounts to terminal connectedness. And this is interesting because it interacts well with the special property of terminally connected geometric morphism, which is the stability property. So in general, connected geometric morphisms, arbitrarily connected geometric morphisms are not pullback stable. And similarly, terminally connected are not expected to be so. But they are stable left to B comma squares. That is, if you have a B comma of this form in the two categories of Grothendieck topoi, with on the right terminally connected geometric morphism, then the corresponding projection also is terminally connected. And this property is reminiscent of something that works for what we call the comprehensive factorization system corresponding to initial and discrete configuration in CAT. And this is what we end. It is known that initial functor in CAT are also stable across the B comma square in the same direction. And this is only because this really looks like, in some sense, terminally connected morphisms are kind of an internalization of what it means to be initial in the two categories of Grothendieck topoi, for the following reason, that if you take a terminally connected geometric morphism and a point, okay, because being initial, it just means that the comma over any object is connected. Empty and connected. And for a geometric morphism, for a terminally connected geometric morphism, if you take the comma at a point, then because of what I just said, you get a terminally connected morphism over set, but because over set there is no difference with connected geometric morphism, this exactly means that the comma of t above x is connected. So you see there is a kind of funny analogy with the initialness. But this is quite subtle because you can show that the functor of point does not send terminally connected morphism on initial functor between category of points. So the relation is subtle. But on the other hand, there are promising aspects because you can show also that pro-etale geometric morphisms are fibration and even in some sense discrete internal configuration and even in some sense discrete configuration. And that's all. And thank you.
You have 1 minute for questions. Any comments? Go ahead.
Is there a particular class of geometric morphisms where the factorization is particularly easy to describe?
You go more generally than the essential. I don't know, but for the local one, you can find a close relation with a restriction where you want to just etale, but open etale at element when you have something which is locally, you can do the same thing for objects that come from the local, and this gives you something which is more akin to the original definition of what Grothendieck, which was considered open a compose at a point and so on. But besides this, I think there was something.
Thanks again.